Hello, everyone. My name is Mohammed Abu Hamid. I'm a PhD student at the University of Central Florida. Today, I'm going to present Multi-X identifying multiple author from source code files. In this presentation, we are going to highlight the problem of authorship attribution in the field of software and the motivation of our work. We'll go through the literature and highlight the challenges and the state-of-the-art methods in the field. We are going to present our work for identifying multiple authors in a single code file, and finally, we will provide the conclusion. First, let's define the problem. Code authorship identification is assigning authors to code samples based on the coding style of programmers. This is based on the fact that programmers tend to develop a distinctive style as they code. And if we capture this feature, we can simply identify the programmers when we see their code. Now, this can be beneficial in the field of software forensics, such as settling authorship disputes or identifying authors of malware. On the other hand, identifying programmers may have privacy implications for programmers who wish to remain anonymous when contributing to open source projects. Working on software authorship attribution is very challenging. In terms of the available samples to attribute, software sample can come with different formats, languages, sizes, and either made by a single or multiple programmers. In terms of coding style, we know that coding style can be language dependent, meaning it changes from one language to another. The coding style can also be continuously evolving and also can be hidden by obfuscation. Most of existing code authorship identification techniques assume a single author per code sample, an assumption that doesn't always hold in real-life applications. For example, modern software projects are often a result of collaborative efforts and teamwork. And this is also true in the malware development community. So addressing a multi-author identification process adds more complication and challenges to the identification tasks, such as defining the size of code segments to be analyzed for attribution. The code segment should be sufficient in size to be accurately attributed and not very large to minimize the probability of being written by multiple programmers. Moreover, the number of contributing programmers to a single code sample can be large, and a multi-author identification system, an effective one, should be capable of identifying code authors even with single line of code. Identifying programmer even with limited information requires powerful tools and abstraction to capture authorship attributes for accurate identification. Now let's see the related work. Studying the field of code authorship identification on the source code, on the software, we can observe many advancements. And most of these advancements are in identifying the programmers of single authored code files. This study addressed many challenges and helped us understand the importance of code representation and authorship attributes for identification process. Some of these challenges are related to language dependencies and extraction of relevant features that can scale to large data sets. And going further, the recent works address the effect of the number of samples per authors for accurate identification and their effect on the accuracy of the identification task. And explored other factors that might affect the analysis, such as temporal changes in the programmer style and the resilience to obfuscation techniques. Besides single author identification method, there are only limited number of multi-author identification techniques, as we can see here. There are two studies, one study on the binary code and another study on the source code domain. Working with the source code domain, the recent study used comprehensive feature extraction process that produce high-dimensional and sparse representation, especially when handling large data set. Moreover, the feature extraction process requires code parsing, syntax tree extraction, and explicit feature evaluation and selection. In our work, we try to reduce the burden of explicit feature extraction process by taking advantage of deep learning to generate high-quality authorship representation that enable large-scale identification. Another difference is that their work achieved an identification accuracy of 99% for 106 programmers, given that each programmer had at least 150 code samples, and using and considering aggregating attributes of multiple samples to get to this accuracy. In our work, we consider identifying authors based on a single sample attribution and raising the challenge to scale even to more authors in open source projects. As you can see, our work achieved remarkable results even when scaling to a larger data set. Now let's have a look at our proposed system. We propose a fine-grained system that includes 5 major steps: code segmentation, code representation, authorship verification, segment integration, and authorship identification. Simply, the system works as follows. We segment the code, let's say line by line, represent these segments as a sequence of word-to-vec representation, and verify the author of these segments using verification models to decide whether 2 subsequent segments belong to the same author or not. If yes, we integrate these segments to a larger segment to have more information for the following steps to work with. After the integration, the integrated segments are fed to the identification model for the identification. For successful design, there are many challenges that we address in the paper regarding the segmentation window, the representation of small segments, size of segments, class imbalance, model architecture for identification, and deep representation. To conduct our experiment and analysis, we evaluated and evaluate our approach. We collected a large data set of 9 large open source projects from GitHub, and we used GitAuthor to obtain the authorship of every line in all files. The collection included more than 26,000 code files and 2,200 programmers. And for our analysis, the first step, addressing code segmentation, we looked at our dataset and observed that multi-authored segments are very common. In fact, code segments with more than 12 lines of code are more likely to be written by multiple authors. Even smaller segments can be written by more than 4 programmers, and this motivates for a fine-grained approach and indicates the challenge in selecting the segment size to be processed. In our experiment, as we will see, we evaluate the effect using different window size to segment the code and their effect on the accuracy of the identification process. The second step is about code representation and how we initially feed code segments to the verification and identification mode. Since we aim to analyze small segments of code, using word-to-vec to represent the code segments as a sequence of term representation makes more sense than using TF-IDF, especially knowing that we have more than 150,000 unique terms in our dataset. And therefore, using TF-IDF would produce large and sparse representation. Working with TF-IDF on the source code domain, the challenge of producing high-quality representation become more obvious, as more than 92% of terms have less frequency than 40 in the entire data collection that we have, as you can see in the figure. We use and analyze utilizing both word-to-vec and TF-IDF as a representation method for the identification task. For word-to-vec representation, we built our own model based on terms that we have in the training set. And for the TF-IDF, we use the top 3,000 features of unigrams, bigrams, and trigrams. The third step is to verify authorship of code segments for integrating and accumulating code lines written by the same author, so the identification model have more information to work with or to attribute or to capture the attribution of authors. This process enables conducting the identification task on larger segments with more information to capture authorship attributes. For this task, we use different model architecture, including long short-term memory, gated recurrent unit, and simple recurrent units. For the verification task, there are many settings we explored, such as the segment size, the model architectures, and many challenges that we address, such as the class imbalance. Please refer to the paper for the full description of how we handle all these challenges. What we see here, the achieved result by different models using different window size for segmenting the code. As we can see here, multi-layer bidirectional LSTM models achieve the best result with an average F1 score of almost 94% when the window size is just one line of code. For segment authorship identification, we also experiment with different model architecture and code representation method. We also show the effect of sample count and the size of samples on the identification accuracy. Based on the ground truth dataset, we obtain the datasets as shown in the table. For example, when selecting authors contributing at least 6 samples with minimum 4 lines of code per sample, the number of programmers is 843 programmers, while there are 282 programmers contributing at least 30 samples with at least 10 lines of code. The goal of this set of experiments is to obtain the best setting for building the identification models and gaining insight on how the sample count and size affect the identification task. Here is our result for identifying a programmer contributing at least a specific number of code samples with different sizes. These results are obtained when using word-to-vec representation as initial representation and multi-layer bidirectional RNN for the identification. We use the multi-layer bidirectional RNN architecture because it shows the best performance on previous experiment. We achieve a higher accuracy than 80% when the programmer contributes more than 20 samples with at least 10 lines of code per sample. Even with the programmer contributing at least 6 samples, the results are very impressive considering the available information. For example, achieving around 75% accuracy when the sample size is at least 10 lines of code. When we use the same settings and only change the representation to TF-IDF method, we can observe an enhancement on the identification accuracy from around 80% to around 84% when the number of samples is higher than 20 samples per program. These results are very good considering the use initial code representation and the use classifier. But we can improve the accuracy even more by utilizing deep representation and robust classifier on top of these deep representations, such as random forest classifier. As we can see here, when we use word-to-vec as initial representation, we can obtain deep representation that enable higher identification accuracy, almost 95%, when the number of samples is higher than 20 samples per author when we use random forest classifier. Even better results are obtained when using TF-IDF as initial representation to generate the deep authorship attributes. The result shows that the model can identify programmers with high accuracy, even when the number of samples as small as 6, and the segment size as small as 4 lines of code, as shown on the top right figure. Building on all these results and experiments that we conducted, we implemented and evaluated the end-to-end fine-grained system. We segment the code line by line. We use our word-to-vec model to represent segments for the verification. We verify segments using multi-layer bidirectional LSTM model and integrate verified segments, and represent the integrated segments with TF-IDF, and obtain the deep representation from the multi-layer bidirectional LSTM of identification model, and then forward this representation to random forest classifier with 300 trees. When we split the dataset by files, we made sure that there is no data leakage between the training and testing phases in all the processes that we conducted. The splitting of the dataset allowed for having 500 62 programmers in the test set of more than 5,000 code files. Our evaluation showed that our system achieved an example-based accuracy of more than 86% and per segment identification accuracy of 93%. Finally, the conclusion. We propose MultiX, a fine-grained system for identifying multiple authors in a single source file. We evaluate MultiX using large data set. For code authorship verification, MultiX achieved an F1 score of more than 93% using multi-layer bidirectional RNN. For code segment authorship identification, the achieved accuracy is more than 96% when authors have at least 30 samples. For the overall system evaluation, we were able to identify multiple authors in more than 5,000 code files with an example-based accuracy of more than 86% and an overall bare code segment authorship identification accuracy of 93. That's our result. Thank you.